Free body diagram. So the term free body diagram, so it means we're drawing a diagram. Obviously, it's a representation. By the body, we're just mean the object, okay? So if we're talking about me holding the iOLAB device in the air, the object is the iOLAB device. So when we use the term free, we mean that it's free from all outside influences. So we're basically taking the object out of its environment and only considering the forces acting on it. All right, so we can represent the body or the object as in a couple ways. We can represent it in the particle method. All right, remember where we just use a dot. Sometimes it's easier just to represent it as like a box. Okay, and so that's how I'm going to do it here, and that makes it especially easier when we're considering representing the iOLAB device too, because it's basically like a little box. All right, so here I'm holding the iOLAB device up in the air. It's stationary. It's not moving. So we could say, first of all, that the net force on it is going to be 0. All right, it's not moving, so the acceleration is 0. So what are all the external forces acting upon the iOLAB device in order for it to be hovering there in the air? So first of all, we know gravity always acts downward. All right, so gravity's pulling downward. And then we can say that there's a tension force upward. So there's a tension from me holding the iOLAB device by the screw. All right, so the screw is kind of the agent that's connecting, that's causing the force upward. Or so it could be my hand and the agent, or my hand and the screw is the agent. All right, but it's basically a tensional force. So I'll call it T for tension. And it's pointing straight upward, exactly opposite gravity. All right, and notice that I tried to make the arrows, the length of both of those arrows to be identical, because remember that the arrows represent the magnitude of the force. So they're basically, everything is motionless, so everything is balanced out. All right, so then what happened before in a previous video when I moved the iOLAB device up and down? All right, so let's consider when I was moving it up. So we still had gravity acting on the device, and there's still a tension on the device, although now the tension has to be much greater than the force of gravity because it's moving upward, all right? And that's what gives us a net force upward, and that's what causes the device to accelerate upward. All right, now how about when I was lowering the device? All right, I had the up and down motion. So during the down part of the motion, what was going on? Again, the same two forces. All right, we have gravity pointing downward. Still have some tension going upward, but not as much. All right, so the gravity arrow is now a lot greater. So our net force is now in the down direction, and so is the acceleration. Now let's consider the scenario where I push the iOLAB device across a flat surface. So before that push, the iOLAB device was just stationary, right? So it was sitting there on a flat surface, not moving. So there was no acceleration, right? There was no net force. It was just sitting there. So what were the forces acting on it? How can we represent that in a free body diagram? So again, gravity pointing downward, and the normal force pointing upward. And I tried to draw them to be the same length because they're the same magnitude, because there's no motion. All right, and there's not really any horizontal motion here yet, right? So let's consider what happened when I started to push on the device. I pushed on it, but I didn't push on it with enough force to get it moving. What was happening? Well, we could say that there was a little bit of applied force, I'll call FA here, that I was applying it to the right, but it didn't apply enough force for it to start moving to overcome static friction. So we could say that my F friction, F of F for friction, was also pushing backward the opposite direction. So, and those two arrows should be basically identical because I pushed, but it didn't quite move yet. All right, pushed a little bit more. Let's say I pushed a little bit more and it still hadn't moved yet. Okay, so I applied a greater force, but it still hadn't moved yet. Well, static friction was holding back with the same amount. So static friction just keeps on equaling the applied force until we reach that maximum static friction, and we overcome static friction, and now we're moving. So what does that look like? All right, so we have gravity always downward, the normal force the same, upward. All right, now once it starts moving, now we have an applied force. All right, and it starts moving, and now we still have friction, but now it's kinetic friction, right? And it's less. All right, so we're accelerating, so that means our acceleration is to the right. So our net force is to the right. Okay, and then this only lasts while I'm pushing on it, while I'm applying that force, and it's accelerating. All right, after that, it kind of reaches basically, for a short period, it reaches a constant velocity, right? And so what does that look like when it's in a constant velocity? All right, so we still have gravity, we still have the normal force, but if it's a constant velocity, the device is moving forward due to that applied force. Friction, kinetic friction is still holding it back, but they're equivalent now, right? So the net force is 0 and the acceleration is 0. So constant velocity means we have 0 acceleration, 0 net force. Okay, and then at some point after that constant velocity, friction is going to take over and start slowing it down. So what does that look like? So then we'll have the applied force still from pushing it to the right, and we'll still have frictional force, but it's going to be much greater now, right? And so the acceleration is now going to be to the left. Right? Sounds a little weird because it's moving to the right, but the acceleration is to the left. So it's like deceleration, we would say. It's negative acceleration. All right, so that also means that the net force is now being applied to the left. So one scenario where it's especially useful to perform free body diagrams is when we have some sort of inclined plane like we studied in an earlier week. So what are the forces going on the iLab device on the inclined plane? Well, if I put it there wheel side down, it's probably going to roll down, right? So what are the forces acting on it? Well, first we have gravity. All right, and then gravity acts directly downward. But the normal force, remember the normal force is always perpendicular to the surface. So we'll draw that. Like that. All right, and then what's happening? All right, what other forces are going on here? Well, we have, there's going to be a frictional force, right, a kinetic frictional force along that direction. So we could say, so now we could see that the direction of the acceleration and the net force is going to be down the plane. Okay, and then if we wanted, we could break down the force of gravity into its x and y components. Right, where this angle is now the same as this angle. All right, and so we basically are setting up the plane. Remember, with our tilted axes we discussed, we're setting it up so the x-axis runs horizontal to the plane, and the y-axis runs perpendicular to the inclined plane. All right, and then we can actually determine what the x components of gravity is there by calculating this side of the triangle there.